we will study about we will look into the difference between the synchronous and asynchronous sequential circuit. So in a synchronous sequential circuit, the memory elements are clocked flip-flops. Here it is either unclocked flip-flop or time delay elements. So in synchronous sequential, the change in input signal will affect the memory element when we activate the clock signal. Here in asynchronous, the change in input can affect the memory element at any time. It does not require the clocking process, and it is the synchronous sequential circuit is easier to design when compared to the asynchronous sequential circuit. The synchronous sequential circuit, the speed depends upon the time delays involved. Asynchronous operates faster than the synchronous sequential circuit. So due to these, some of the advantages, uh, these are classified into synchronous as well as asynchronous. So in asynchronous sequential circuit, there are two types, that is pulse mode circuit model and fundamental mode circuit model. So in order to ensure proper operation, it is necessary for the synchronous sequential circuit to attain a stable state before the input is changed to a new value. So because of the unequal delays in the wire and gate circuits, it is possible to have two or more input variables change at exactly the same input. So therefore, the simultaneous changes of two or more input variables are usually avoided. So in other words, we can say that only one input variable is allowed to change at any one time, and the time between the two input changes is kept longer than the time it takes the circuit to reach a stable state. According to how the input variables are to be considered, there are two types of asynchronous circuits. First one is the fundamental mode circuits, and the next is the pulse mode circuits. So fundamental mode circuit, it assumes that input changes should be spaced in time by at least delta t, the time needed for the circuit. The delta t is the time needed for the circuit to settle into a stable state following an input change. That is, the input variable should change only when the circuit is stable. Only one input variable can change at a given instant of time. The inputs in the fundamental mode circuit are levels, it is not pulses. Delay lines are used as the memory elements. The next one is the pulse mode circuit. Here the input variables are pulses instead of levels. So the width of the pulses is long enough for the circuit to respond to the input, and the pulse width must not be so long that it is still present after the new state is reached. So the pulses should not occur simultaneously on two or more input lines. The flip-flops are commonly used as memory elements here in the pulse mode circuit. The memory element transition are initiated only by the input pulses. These input variables are used only in the uncomplemented or the complemented forms, but not both. So these are the cases when compared to the pulse mode circuit. So there are several steps used for the design of asynchronous sequential circuit. So first step is the construction of primitive flow table. That flow table is identified from the problem statement given, and an intermediate step that may include the development of a state diagram. Second step is the reduction of primitive flow table. So here the primitive flow table that is constructed in the first step is reduced by eliminating the redundant states by using the state reduction techniques. And third, doing the state assignment. Fourth step is this primitive flow table is realized using the appropriate logic elements. So derivation of primitive flow table. So we'll see how the primitive flow table is derived. So initially, from the problem statement, the flow table is same as that of the state table in the synchronous sequential circuit. So in asynchronous, the state table is known as the flow table because of the behavior of the asynchronous sequential circuit. The state changes that occur independent of clock based on the logic propagation delay and causes the states to flow from one to another. So this primitive flow table is a special case of a flow table. So again, it is defined as a flow table which has exactly one stable state for each row in the table. The design process begins with the construction of primitive flow table. So first step is the construction of primitive flow table. So this is the problem statement given. We have a different states such as A, B, C, D, E, F, G and H. We have several inputs for which each output is represented in the diagram. So using this state diagram, we are going to draw the primitive flow table. So this is the primitive flow table. Here the present states from A to H are considered, and the next state is obtained from the state diagram. The input and output also obtained from the state diagram. So for each row there is one stable state. For a first row, for A row there is one A state. For B row there is one B state. For C row there is one C state. Similarly, up to H there is only one stable state for each row. So this is called as the primitive flow table. So next step is the reduction of primitive flow table. So it is to reduce the primitive flow table using state reduction technique. So how to reduce the primitive flow table? So this process is done by using a tool called as merger graph. So we are going to use the merger graph technique to reduce the primitive flow table. So merger graph is state reducing tool that is used to reduce states in the incompletely specified machine. So how this merger graph is defined means, so there are several cases. So first case is it contains the same number of vertices as the state table contains states. So each compatible state pair is indicated by a line drawn between the two state vertices. Every potentially compatible state pair with outputs not in conflict but whose next states are different is connected by a broken line. Then the next case is the implied states are drawn in the line break between the two potentially compatible states. So if in last cases, if two states are incompatible, no connecting line is drawn. So these are the cases for drawing the merger graph. Using this merger graph, we can simplify the states. So this is the reduction of primitive flow table using merger graph method. So the compatible and incompatible pairs are written here. A, B, C are compatible, which is denoted as S0. D is incompatible with any other state, so it is S1, and E is also denoted as S2. Similarly, alternative method is also mentioned, and the particular variables are replaced with the new variables such that more number of states are reduced finally into 3 states. So after this, we need to identify the races and cycles. So in the races, race denotes race. The definition of race is when two or more binary state variables change their value in response to change in input variable, race condition occurs in the asynchronous sequential circuit. So we have to find out from the situation where the races occur. For example, if change in two state variables due to change in input variables such that both change from 0, 0 to 1, 1. So in races, we have two types, critical as well as non-critical races. So critical races must be, may be harmful, so it must be avoided for proper operation. Then cycles. So in cycle, the definition is the cycle occurs when asynchronous circuit makes a transition through a series of unstable states. So when a state assignment is made so that it introduces cycle, care must be taken. So if a cycle does not contain a stable state, the circuit will go from one unstable state to another until the inputs are changed. Then there are two techniques commonly used for making a critical race-free state assignment. One is the shared row state assignment, and other one is the one-hot state assignment. So in shared row state assignment, the state variables are assigned with binary numbers in such a way that only one state variable can change at any one time when a state transition occurs. So in order to accomplish this, it is necessary that states between which transition occur be given adjacent assignments. Two binary values are said to be adjacent if they differ in only one variable. So this extra state is shared between the two stable states. And the another method is called as one-hot state assignment. In a one-hot state assignment, only one variable is active or hot for each row in the original flow table. That is, it requires one state variable for each row of the flow table. Additional rows can be introduced to provide single variable changes between internal state transition. So this comes under the one-hot state assignment. The figure denotes the transition diagram with the race and without race. So addition of one stable state will be eliminating the presence of races.